Good day, everyone. This is Professor Friday coming at you one more time. Today we are going to be talking about volume according to the technique of cylindrical shells. So today we're going to be finding the volume of the solid generated by rotating the region between the x-axis and y equals 3x squared minus x cubed about the line x equals 3. First thing I want to do is get an idea of what this thing looks like. So you can either graph this by hand or you can use a graphing calculator to help you out. But this is a cubic that looks approximately like this. The region in question is the region that is between the x-axis and the curve itself. So we're talking about this right here. And we're going to be rotating that about the line x equals 3. Coincidentally, that happens to be where one of the intercepts is for this curve. I'm just kidding. That's not a coincidence. That's actually a pretty typical thing that we do. So before we get to that, I want to briefly cover what it is to have the volume of a cylindrical shell. So a cylindrical shell looks approximately like this. Forgive my horrible artistry skills. So this is a cylindrical shell. And the volume of a cylindrical shell is equal to 2 times pi times the radius of the cylindrical shell times the height of the cylindrical shell times the thickness of the cylindrical shell. Now, depending on your axis of rotation, the thickness is always guaranteed to be either delta y or delta x. Now, if you wanted to remember this a little more compactly, then 2 pi times the radius, you could also refer to that as the circumference. So, circumference. I should probably know how to spell that as a mathematician, shouldn't I? I think that's right. Circumference of the cylindrical shell. Alright, so here's what's going on. What we're going to do is our region in question. First thing you'll always want to do is grab a sample rectangle. It's a little tiny rectangle, just like so, that creates the cylindrical shell by rotating it about this axis. So what I want to do is draw this sample rectangle within the region over here so that we can get an idea for what it looks like. So generally your sample rectangle, depending on whether you're doing cylindrical shells or discs and washers and you have a vertical axis versus a horizontal axis, well, for the vertical axis of rotation, like we have at x equals 3, the orientation of the sample rectangle is going to be vertical, with the thickness being a little tiny change in x. So when I rotate this little rectangle about this axis, yeesh, that's an arrow, we're going to get a little tiny cylindrical shell that looks like this. I want to see if we can come up with the expression for what this cylindrical shell would look like. So we said that the volume of the cylindrical shell is going to be 2 pi times the radius times the height times the thickness. Now, what we just established is that the thickness here is a little tiny change in x. Like I said, it'll always be a little tiny change in x or a little tiny change in y. Now, something tricky here is going to be the radius, because the radius is the distance from our axis to the exterior. Now, generally, when you're just revolving around the y-axis, the radius would simply be the horizontal distance from the axis to this, which would be x. So this distance right here would be x. But that's not where our axis of rotation is, because we know that this distance right here is 3. Your radius is actually this guy right here. So setting up a little expression based on this, x plus the radius would have to be equal to 3. Therefore, your radius is equal to 3 minus x. That's going to be an important thing to have in our calculation here. So we got 2 times pi times the radius. The radius is going to be 3 minus x. Now for the height of the cylindrical shell, you see that the height of the sample rectangle just extends from the x-axis up to the curve itself. Well, that would be y. So the height is equal to y. However, we also know that the thickness is delta x, which means that everything here needs to be in terms of x not in terms of y. However, the curve was given to us back up here, y is equal to 3x squared minus x cubed. So that will be our height. And then, as we already stated, the thickness is going to be delta x. So this is your volume expression for a single cylindrical shell. Now, we're interested in all of those cylindrical shells, but we know that if we take an interval like this, we chop it up into little bitty pieces, figure out the individual volumes and add them together, that's just the idea of a Riemann sum, which gives us a definite integral. So the volume of the actual region, or volume of the solid itself, is going to be equal to the definite integral. Now, for the limits of integration, the interval starts here and ends here. We established that these would be the x-intercepts of the curve. So with a little bit of algebra, you could show that the x-intercepts of this function are 0 and 3. Kind of implied already in the problem though. So limits of integration 0 to 3 of 2 pi times the radius, 3 minus x, times the height, 3x squared minus x cubed, times the thickness. And as soon as we take that limit and turn it into an integral rather than just our Riemann sum, our delta x is going to become a dx. So, when it comes to these problems, I can guarantee you that the setup is harder than the actual integral itself. So, I'm going to let you take care of evaluating this integral. I hope this was helpful. I'll see you again soon for another tutorial.